Hi, this is Group 3, and we have Molly, Jean, Winnie, and Emma in this group. Today we're going to explain the question step by step and have an expanded discussion on the idea of this question. So this is the question we're going to explain today. You can pause the video to read through the question slowly. So this question is about Kepler's third law. The idea is a spaceship is moving in a circular orbit around Earth with radius r and its period is t. At some point, it slows down at position A and enters an elliptical orbit to return to Earth. This new orbit touches the Earth's surface at point B, which means the closest point of the ellipse is the Earth's radius. That's called at capital R, and the farthest point stays at R. Now, in an elliptical orbit, the semi-major axis is the average of the closest and farthest distances. So here, the semi-major axis is open parenthesis r plus capital R close parenthesis divided by 2. Kepler's third law tells us that the square of the period is proportional to the cube of the semi-major axis. So we write t prime square is proportional to the sum of r and capital R, divided by 2, then cubed.
The question says the spaceship travels from A to B, which is half of the ellipse, and it takes 3 times square roots of 3 over 16 big T to do that. So the full orbit would take 3 times square root of 3 over 8 times T. Now we plug that into the equation. Open parenthesis r plus big R divided by 2 close parenthesis to the power of 3 divided by r cubed equals open parenthesis 3 times square roots of 3 over 8 close parenthesis squared. We simplify that right hand side. 3 squared is 9, square root of 3 squared is 3, and 8 squared is 64, so the whole thing becomes 27 over 64. Now we multiply both sides by r cubed and solve the equation. After simplifying everything, we find that r over big R equals 2, so the answer is choice B, 2.
Next, we introduce a commonly used best maneuver, the Hohmann transfer orbit. The Hohmann transfer is the most fuel-efficient orbital maneuver, used to transfer a spacecraft from one circular coplanar orbit to another. The process requires only 2 propulsion maneuvers. The first propels the spacecraft into an elliptical transfer orbit that is tangent to both the initial and target orbits, and the second adjusts the orbit upon arrival to match the target orbit. This method is commonly used to transfer satellites from low Earth orbit to geostationary orbit. Then we take the transfer from Earth to Mars as an example. It is known that Earth's orbital radius is 1 astronomical units, and Mars' orbital radius is 1.524 astronomical units. By adding both radius and dividing by 2, we get the semi-major axis of the Hohmann transfer orbit as 1.262 astronomical units. According to Kepler's third law, t squared equals r cubed. We can calculate the period of the elliptical orbit to be 1.417 years. Since the spacecraft only needs to travel half of the elliptical orbit, the actual flight time is 259 days. To ensure the spacecraft reaches Mars precisely after 259 days, it must launch at a specific time, known as the launch window. At this time, Earth must be approximately 44 degrees behind Mars. This usually occurs about 100 days before Mars reaches opposition. The cycle of this launch window is the synodic period between Earth and Mars, which is about 780 days. Of course, these are also limitations of using the Hohmann transfer orbit, including the long waiting time due to the lengthy period, and the fact that it is not ideal for urgent missions. Additionally, the angle and timing must be calculated with extreme precision, leaving very little margin for error.
An example of a mission that applied the principles of the Hohmann transfer orbit is NASA's Perseverance rover. It was launched on July 30th, 2020, at 7:50 a.m. during the launch window. However, because most modern space missions are goal-oriented and do not require the same level of fuel conservation, the Perseverance mission did not use a purely Hohmann transfer orbit. Instead, the trajectory was adjusted and optimized based on the theoretical models to shorten the flight time and meet mission requirements. So during the journey to Mars, Perseverance underwent several orbital adjustments due to the various uncertainties in space, such as the relative motion of planets and propulsion system issues. The landing on Mars also involved a critical period known as the 7 minutes of terror, as Perseverance entered Mars' atmosphere at a speed of about 20,000 km per hour. The atmosphere on Mars is much thinner compared to Earth, only about 1% of Earth's atmosphere. Therefore, a heat shield capable of withstanding high temperature is required to protect the spacecraft. Without it, the spacecraft could burn up due to the rapid friction with the thin atmosphere. Consequently, Perseverance first deployed its parachute. Then the sky crane system was activated, using rocket engines for final deceleration and precise adjustments of its position and orientation, ensuring that the spacecraft hovered stably and safely touched down on the Martian surface. Once Perseverance made contact with the surface, the cables from the sky crane were quickly severed, and the platform retracted, completing a precise and safe landing. So all in all, as we introduced before, the Hohmann transfer orbit plays a crucial role in exploring the space and exploring the place out of planet. We hope you have learned something new through our introduction. Thank you for listening.